All right, ladies and gentlemen, today we're going to be talking about how electrons and atoms behave like waves. We've mentioned that the wave model is the current accepted model defining where electrons are around a nucleus, which was an expansion on Bohr. So this is a rather in-depth video that's going to hit a lot of ideas. So you'll notice that we're going to make connections to several of the objectives on our list. So you're going to be looking for connections between objectives 4.8 to 4.13. Make sure you recognize and can find in the notes where we address each of these different objectives. When we look at electrons, they are able to absorb or release energy. What we've noticed is that the energy they carry is related to their location or position around the nucleus. If they gave energy, they are going to be able to move further from the nucleus. So remember we said the energy levels are related to how close or far they are from the nucleus. Now when talking about a wave, there are several different features we can define or identify. Wavelength is the length of a complete wave, so it's kind of built into the word. That symbol that you see is called lambda, so that's going to be the symbol we're using for wavelength. Frequency is how many waves pass a certain point in a time period. The most common unit for this is the hertz, where it's 1 wave every second. So we're looking for how many times a wave will pass per second. Amplitude is the distance from the origin to the trough or crest. You can think of this as giving some information about the intensity of the wave. So here we see different regions identified. So the crest would be the peak of a wave, the trough is the bottom. The origin would be kind of that middle ground, the point in the middle that the wave starts. A wavelength is from a crest to a crest or a trough to a trough. Amplitude is the height, you could think of it, from the origin to a crest or from the origin to a trough. So here we see that this wave is a little bit closer together than the one above it. This would be a higher frequency wave at this point. So what we see is because they are closer together, they're going to pass the same point more often, which is where we get that idea of a higher frequency. The frequency is related to the color of light in the visible light spectrum. Now, when we take a look at the electromagnetic spectrum, high energy waves are above the violet. That's why we call ultraviolet, the region right by the visible light, ultra, because it's above. So when you look to the left of this diagram, those are high energy waves. The higher energy actually makes them more dangerous. That's why we care about ultraviolet exposure in terms of cancer. The high energy waves can actually damage your DNA. Now looking at the red end, this is our low energy waves. You'll notice that the region below it is called infrared or below red. These are where we start to get more of like heat types of things. They are lower energy waves, so they are less dangerous to us. You'll notice on these diagrams, keep in mind that we flipped the sides. So this time the high energy is on the right. The visible range is a very, very small portion of the electromagnetic spectrum. So the part that you can actually view in terms of color represents a very, very small range of frequency and wavelength. So radio waves, microwaves, those are low energy. Notice they're more spread out. So the wavelengths are very long and their frequencies are low. Higher energy waves thinks about they're going to hit you more often. That short wavelength and high frequency, think of it as like hitting against you faster. So those higher energy waves have short wavelengths and high frequency. Now when we look at the spectrum, we can look at it in terms of frequency or wavelength. So we said those two things are going to be held together in a relationship. So with frequency and wavelength, we're going to be able to make connections between how they are changed in terms of the energy of the wave. Now, for my regular students, you are not going to have to do these calculations. So you can kind of pick up in a little bit. I still want you to be aware of the idea that these are related together. The speed of light is going to be the constant between frequency and wavelength. For my honors kids, you want to be listening very carefully. So C is a constant, meaning it will always be the same. It's a known value. This is a number you will have to know. So 3 times 10 to the 8th meters per second is the value of the speed of light. Wavelength is lambda. You can measure that in meters or nanometers, but you'll notice based on the given value of the speed of light, you'll have to convert to meters. So nanometers would be 10 to the -9th, just to keep that in mind. Frequency, remember we said in hertz, is 1 per second. That is significant in the canceling out of units. So let's say I told you to find the frequency of a photon with a wavelength of 434 nanometers. We don't know the frequency. We know the wavelength. If it's 434 nanometers, that is 4.34 times 10 to the -7th meters. We do know our constant for the speed of light. So if we plug that into our values and rearrange to solve for frequency, we would get C divided by lambda. When we plug those values in, we would find out that our frequency would calculate to 6.91 times 10 to the 14th hertz. It is very important that you attempt to calculate these values, because if you do not plunge it into your calculator correctly, you can get a very odd exponent. So 10 to the 14th is your correct exponent. Remember that nanometers is 1 times 10 to the -9th meters. Or I'm sorry, 1 nanometer is equal to 1 times 10 to the -9th meters. So let's take a look at an example element. Iron emits light when it's heated. As it gains energy, it starts to emit different colors of light, and each color has a specific wavelength or frequency. We can match that up to the spectrum. So what scientists have concluded is that if only specific colors are emitted, atoms must only gain or lose energy in specific amounts. Otherwise, I'd see a whole range of colors. They've identified those amounts as quantas. Think of like quantity. So enter Planck. In terms of the quantum theory, and this is where my regular students should be picking back up again, what we observed is that light was emitted from hot objects. That's something that made us ask questions. So based on our observations, we concluded that energy is emitted in specific amounts. And a quantum was defined as the smallest possible amount that energy could be emitted in. Remember how we talked about electron mass? And some of those experiments allowed us to calculate a single electron's mass. Same idea. There is a smallest known emission of energy. So think if we wanted to go up a hill, and that hill represented an amount of energy. A hill would be a continuous emission. You could stop at any point along that hill. What Planck suggested is that's not how it works with atoms. Oops. Think of it as I can only go up one stair at a time. You can't be halfway between a stair if you're thinking about trying to stop there. You could, but it'd be difficult. You're either on one stair or the next. So the height of the stair represents that amount of energy that atoms emit in. Einstein noticed more evidence to suggest the same ideas. He saw that a photoelectric effect occurred when he ran electricity through a cathode and was able to look at how the stream of electrons affected the metal. He was able to see a pattern or a relationship between the wavelength of light emitted and the types of elements. Which brings us to our ultimate theory. If we have light reacting kind of like waves and particles, because we saw patterns in the frequency and the wavelength, but we also saw the emission in the terms of particles, Einstein identified that it can act as both. So we can identify the electron behavior. We see that they have subatomic particle properties, but it also has evidence that they act like waves. We gave a name to a particle of light that carries a single quantum of energy as a photon. So a photon is a particle. Think in the way that like an atom is one type of particle, proton is a type of particle, so are photons. And they carry a specific amount of energy. So let's say I was going to add some energy to an atom. It's going to cause it to have the electrons move to higher energy levels. They're able to be further from the nucleus. So I could do that through heat, or I could add electricity. When that electron stops getting energy, it's going to fall back to its original energy level. When doing that, it's going to release the energy it absorbed. Again, it can only gain or release energy in these specific quanta. Sometimes we can see it if it's in the visible spectrum. Sometimes we cannot if it's outside that spectrum. But once that energy source is taken away, the electrons will release what they gained and fall back to their normal energy level. So, for my honor students, for calculations, the energy, the amount of energy in a photon is related to frequency and something called Planck's constant. Remember, he's one of those first guys that told us there is this observed relationship. So energy is measured in joules, capital J. The Planck's constant, we got that awesome scientific notation there. It is joule seconds, 6.6262 times 10 to the negative 34th. No, it's a very, very, very small number. And frequency from before is measured in hertz. Remember, that's a unit that involves 1 per second. So if we have a red photon with a frequency of 4.57 times 10 to the 14th hertz, and I want to know the energy, we are given the frequency and we know our constant. H, just like C before, is a constant that we know. When we plug into the equation, we would multiply Planck's constant times the frequency, and our answer would be 3.03 times 10 to the negative 19th joules. So remember, joule seconds times 1 per second will cancel out the seconds units and give us joules. Please make sure again that your calculator correctly can get you that number. If not, see me in class. So one of the coolest labs that you guys probably will do this year, we're going to actually be burning some metal salts dissolved in water. And we're going to look to identify what colors those salts release when they're burned in the flame. That will be able to tell us some information about the kinds of energy that's released by those different types of elements. So the energy released is going to tell us a little bit about where the electrons are in the atom in terms of electrons and light. When we look at the light that's coming out of the fluorescent lights in the classroom, we know it's the continuous visible spectrum. It has all of the red through violet light. We said, though, that electrons will absorb in specific amounts. So when we look at elements, they actually emit certain wavelengths instead of all of them. Now, an emission spectrum is the name we give to the pattern of wavelengths that is emitted by an element. Each element has a different pattern of wavelengths because they all have different numbers of electrons. The more electrons you have that can move around in the energy levels, the more emission lines you're going to see. So what's happening is we're going to excite the electrons, add energy in, and then as they fall back down to their original energy level, they're going to release that specific quanta of energy. Again, because this is specific to the electron arrangement, this is like a fingerprint for the different elements. So, during the flame test lab that we're going to do, we're going to cause the electrons to jump energy levels and then fall back down. So when they're in the flame, they're taking in that energy, they're absorbing, and then as they fall back down, that is when they release the colored light. There are 3 terms that are connected to this movement in the energy levels. When we look at energy levels, those are those regions around the nucleus that can exist and hold different numbers of electrons. That was the part that Bohr got right. Remember though, they're not orbits, they're more like clouds. Ground state would be a normal atom's state of